Right. So, before the break we had obtained the diffusion equation as the first derivative of the probability is equal to 1 by 2 into the second derivative of the probability with respect to the space variable. Now, our next issue is to solve the diffusion equation. We shall do so using the Fourier transform, which is the most elegant method perhaps to solve this particular equation. There are other methods like separation of variables, but this happens to be a very elegant and a very precise method of solving this diffusion equation. The Fourier transform of a given function f x of x is defined as f hat k is equal to this expression integral f x e to the power minus I k x dx, and the inverse Fourier transform is given by f x is equal to 1 upon 2 pi integral of f k f hat k e to the power I k x d x dk I am sorry dk. So, our given equation is dp upon dt is equal to 1 by 2 d square p upon dx square. We take the Fourier transform of both the sides. On taking the Fourier transform of both the sides, if you look at this carefully, let us look at the left hand side carefully. The derivative is with respect to t and the integral is with respect to x. So, we can take the derivative outside the integration without any problem, and whatever remains inside the integral is nothing but the Fourier transform of p. So, we can write it as del by del t of p hat or the Fourier transform of p k t. And if you look at the right hand side, the right hand side contains the second derivative of x, and this x will operate on this exponential term which contains the x, and it will differentiate it 2 times, and we shall have minus k square upon 2, and what will remain then is the 1 by 2 term will be there as it is, and the second this term would have been annulled by the operation on this exponential term, and what is left is now p x t e to the power minus x t dx into k square, which k square has already come outside, minus k square which has already come outside, and so what remains is nothing but the Fourier transform of p. Now, the solution of this equation, it is a first order differential equation in time, it is a partial differential equation in time, it is quite simple, and we get p hat of k t is equal to p hat of k 0, which is the initial condition, into e to the power minus 1 by 2 k square t, that can be obtained by simple integration. The initial condition, as we had discussed earlier, is p x 0 is equal to delta x. If you take the Fourier transform of both the sides, the Fourier transform of delta x is delta hat k, which is equal to 1. Fourier transform of delta x is equal to 1. Therefore, the solution by substituting this of this equation becomes p k t is equal to e to the power minus 1 by 2 k square t. Now, we take the inverse Fourier transform. When we take the inverse Fourier transform, we get p x t is equal to 1 upon 2 pi e to the power this expression into I k x d k, and this is equal to, when you simplify this integral is converted it into a perfect square, take this expression outside which is independent of k, this expression is independent of k. So, you can take it outside the integral and you are left with this expression inside the integral as a perfect square, and this is nothing but a Gaussian integral, and using this Gaussian integral as under root 2 pi we get the simplification of this whole expression as 1 upon under root 2 pi t e to the power minus x square upon 2 t. This e to the power minus x square upon 2 t is what we had here. We had here this expression, and the under root t has come from here, under root t has come from here, this in the denominator, this 2 pi, the square root of 2 pi has come from the cancellation of the square root, which is the value of this Gaussian integral with this one, and we end up with this expression as the inverse Fourier transform solution of this. And if you recall, this is clearly the PDF of a normal distribution with a mean of 0 and with a variance of t. So, that establishes that the variable that we were talking about is normally distributed with a mean of 0 and a variance of t, which is nothing but a Brownian motion, which is exactly what we wanted to establish. Now, before I proceed further, I would like to discuss an example, an illustration of the central limit theorem. As I mentioned, it is slightly obscure. I will not go into the proof of this theorem, but I will give you an example which makes it very clear, or makes it very conspicuous that this central limit theorem has a significant relevance, and the cardinal property of the central limit theorem, and that the underlying distributions of the variables is irrelevant, is clearly exposed by this particular example. So, we have got random variables x I, capital X I is 1 to n. Later on we will take the limit as n tending to infinity, but for the moment let us keep it finite. So, x I equal to 1 to n are uniformly distributed. All of them are uniformly distributed, random, identical, independent, identically distributed variables over the interval 0 and 1. They are uniformly distributed IIDs over the interval 0 and 1. So, one obvious thing is that 1 is equal to integral this of this way, and that gives us p x I is equal to 1. In other words, the probability density function of each of these variables is equal to unity. Probability density function of each of these variables as seen from this integration is equal to unity, each of these variables. Now, the mean of each of these variables, as you can see, using p x I is equal to 1, this turns out to be 1 by 2. The mean of x I square is x I square p x I, as you can see, it turns out to be 1 by 3, and therefore, the variance turns out to be 1 by 12 for each of these variables. X 1, x 2, x 3 each has a mean of 1 by 2, each has a variance of 1 by 12. Let us define the variable z n equal to, remember this is something to do with the central limit theorem, as we have mentioned earlier. So, we define the variable, the random variable capital Z n. Now, please note the difference between capital Z and small z, and capital X and small x. Capital X is the random variable, small x will represent the values that the random variable capital X can take. So, small x is the spectrum of values that the variable capital X can take. Capital X is the symptomatic variable, random variable. So, z n is equal to x n minus n mu, which in our case becomes n into mu is equal to 1 by 2 for each of the x I. So, it becomes n into 1 by 2, and similarly sigma square is equal to 1 by 12. So, it becomes under root n by 12. The probability density function of z n is given by rho z is equal to the integration of all the probability density functions of all the random variables involved in this, and this because this is z is a sum of a number of random variables x 1, x 2, x 3, x n. Therefore, the probability distribution of z is given by this integration p x 1 dx 1, p x 2 dx 2, and p x n dx n, but with this qualification. What does this qualification mean? This qualification means that in this integration only those values should contribute where this z is equal to z n. In other words, only those contributions will contribute to this integral, to this probability density function where this condition is fulfilled. It is not a general overriding integral of all these expressions, it is an integral which is confined to only those values where this constraint equation is satisfied. This is a manifestation, this delta function is a manifestation of this constraint, that this constraint has to hold. Now, PDF of each of these xi is 1, we have already discussed that it is unity. So, we can throw away this px1 px2 and we have this expression as the PDF of z. Now, this delta z minus zn can be written as a Fourier representation of the delta function as 1 upon 2 pi integral dk exponential I k z minus zn. So, substituting this value here, the integral becomes this expression. And now, we do some simplification. If you look at this, I k z is here and this z n, I have simply put the value here. Z n is equal to this expression, we started with that. Now, further simplification, if you look at this, I take this expression and this expression and together with the z and the sigma xi's, I take them separately because they are going to contribute elsewhere. So, this n by 2 upon under root n by 12 gives me this under root 3 n, and this expression has come from here and this expression as it is I have taken. Now, if I open the summation, now if you look at this carefully, all these integrals are same. So, if all these integrals are same, I can combine them and I can put them to the power n. Now, let us look at this integral which I have taken as power n. Let us evaluate this particular integral without the nth power. This, let us call this I, this integral I, and let us evaluate that. When you evaluate this integral exponential I k x under root n by 2, you get after some simplification, taking 0 to 1, and you end up with this particular expression. It is quite straightforward, the integration is quite straightforward, it is an exponential. So, it is not very difficult and you can get this expression in terms of sine of this upon this, sine theta upon theta, it is of the form. Now, so you substitute this value here and take the power n, get back the power n. If you look at this carefully, this expression when raised to the power n, it gives you the same expression as this under root 3 n with a minus sign. So, this exponential plus under root 3 n gets annulled by this minus under root 3 n, which is combination of this n and this expression, and we are left with integral of dk sine of this upon this to the power n. This expression and this expression get cancelled out with this n also. And now, you can expand this sine theta in terms of theta minus theta cube upon 3 factorial and so on, and you arrive at this expression. By if you take the first two terms only, sine theta is equal to theta minus theta cube upon 3 factorial, and so this sine theta upon theta gives you 1 minus theta square, sine theta upon theta gives you theta square upon 3 factorial, and that is precisely what is here, and theta is nothing but this expression. Now, this taken to the power n taken with the limit n tending to infinity gives me this and gives me this expression. Substitute this here, do the squaring and simplification, and you get this expression, and again you end up with what is this? This is nothing but the PDF of the standard normal variate. So, a lot of manipulation and we end up with the standard normal variate. The limit is taken at this point. Prior to this, we had not taken any limits. At this point, we take the limit as n tending to infinity, and we end up with this particular expression for the probability density function of z, this, which is nothing but the standard normal variate. So, how interesting it is, you started with n uniformly distributed variables in 0 1 and you ended with the normal distribution minus infinity to plus infinity, it can take any values. So, this is the beauty of the central limit theorem. The central limit theorem does not depend on the distribution of the underlying variables which are being added to form the the variable whose distribution is is being considered. The underlying distributions are irrelevant, but what we want is two things: the mean and variance should be finite, and number two, the variables should be IID, independent, identically distributed variables. Now, let us go back to Brownian motion. We have digressed a lot. Let us go back to Brownian motion. Brownian motion, as I mentioned, as I briefly touched upon while talking about random walks, we can have random walks with scaling. The normal scaling that is there for Brownian motion is under root t upon n, but we can add a factor sigma. By adding this factor sigma, we are able to adjust or manipulate the dispersion of the data on which we want to fit the Brownian motion or which we want to describe by the stochastic process using Brownian motion. So, by introducing the sigma any real value, you can adjust or adapt the concept of Brownian motion to fit in variety of data. Not only that, you can add another non-stochastic term mu dt, where mu is the rate of change per unit time of the variable. So then you have a combination of a non-stochastic term and a stochastic term. The stochastic term is scaled by sigma, and the non-stochastic term has a mean rate of mu, and it is scaled by dt. It increases as time progresses. So, this is called generalized Brownian motion. Brownian motion with drift, this is the drift term, this is drift and this is diffusion. Mu dt is the drift term. So, this is called Brownian motion with drift, or it is also called the generalized Wiener process. What are the parameters of the generalized Wiener process? It is quite obvious. The mean is given by this. This has a mean of 0. You see, this has a mean of 0, and since this has a mean of 0, this term will not contribute, and therefore, we have a mean of mu dt. And what about the variance? The variance, this is non-stochastic. This is non-stochastic, so it does not contribute to variance, and this expression has a variance of t, and when you add this or dt, this expression has a variance of dt, and when you introduce this, scale it with sigma, the variance becomes sigma square dt. So, the variance is sigma square dt, the mean is mu dt. This is an example of Brownian motion with drift. It is an upward drift here. You can clearly see that there is a trend emanating. The Brownian motion is random, it is fluctuating, but it is fluctuating with a clearly perceptible upward bias, and that is what is called a Brownian motion with drift. Of course, the drift can also be negative. Nobody prevents you from having a negatively biased Brownian motion. Drift rate, the mean change per unit time of a stochastic process is called the drift rate, and the variance per unit time is called the variance rate. So, the mean change per unit time is the drift rate, and the mean change and the variance per unit time is called variance rate. We also have exponential Brownian motion. Look at this, it is behaving like there is an underlying exponential curve, and it is fluctuating about that particular exponential curve. You can clearly see that the zigzag is there, but the zigzag is superposed on a certain exponential curve or an exponential underlying progression. Further generalization of the Brownian motion. Now, so far we have been talking about we just now talked about mu dt plus sigma dw. Now, in this case sigma and mu were constants, they were not functions of x or t, they did not change with time or with the stochastic variable, but you can have stochastic processes where both these quantities mu and sigma are functions of x and t. These are called Ito processes, where the drift as well as the diffusion or the variance are functions of x and time the process is called Ito process. Now we come to a very interesting concept. You see, we have been talking about Brownian motion throughout. Now we want to extrapolate that and talk about functions of Brownian motion. We want to talk about calculus of Brownian motion. The question is, why do we need a separate calculus for Brownian motion? Why not use the contemporary calculus that we have for Brownian motion? Why use a new calculus? Let us see the answer to that. Let us say we have a simple function of Brownian motion, f w t is given by w t square. Therefore, we have d of w t square, the derivative of w t square is 2 w t t w t. So far it is quite straightforward. This is just like any classical function, any Newtonian function, d of x square is equal to 2x dx. d of x square is equal to 2x dx, right. Let us see whether this is the correct representation of a Brownian function. For this, what we do is we evaluate the expected value of both the sides. Let us start with the right hand side. For this purpose, what we do is we partition the interval 0 to t, 0 to t into n parts, 0 t upon n, 2 t upon n, and the last part is n t upon n, that is t. In other words, the time of observation, time t, is being partitioned into n slices and disjoint slices, disjoint parts, 0 t upon n, 2 t upon n. Now, let us look at this. 2 w s t s integration between 0 and t. Let us look at this expression, then we will evaluate its expectation value. Writing it as the sum of a series, integration can always be written as a sum of a series with taking the limit as n tending to infinity. So, we do that, we write it as the sum of a series, we write it as w at the value at the beginning of a partition into the increment over that partition. So, value at the beginning of the partition into increment over that partition, just like this, value at the beginning of the partition, increment over that partition, value at the beginning of the partition, increment over the partition, and we take the total sum. Now, look at this, take any arbitrary term, let us say we take this term. Now, by the properties of Brownian motion is a Markov process. The further development of a Brownian motion, the further evolution of a Brownian motion does not depend on its past history. Therefore, what does it mean? It means that this expression and this expression are independent of each other. This is the further development of Brownian motion from this point onwards. Therefore, this development is independent of what has happened earlier, what has happened up to this point. Therefore, because these two are independent, the expected value of this into this will be equal to the expected value of this into expected value of this. Now, all of us know that the expected value of a Brownian motion increment is 0. The expected value of a Brownian motion increment is always 0. Therefore, this expression is always 0, and hence the whole thing vanishes. Now, this is any arbitrary element of the sum, any arbitrary element of the sum. So, what does it mean? It means that this whole expression is a sum of zeros, and therefore, it is also 0. So, the expected value of this is equal to the expected value of this expression is equal to 0. So, the first thing that we have concluded is that as far as this integral is concerned, the expected value of this integral is equal to 0. Now, let us look at the second integral. Second integral is integral 0 to t d w s squared, because we what did we say? We said that d of x square is equal to 2x dx, and then dx, and then we integrate over 0 to t, integrate over 0 to t, that is what we have done. So, this we have shown as 0, the right hand side we have shown as 0. Now, we attack the left hand side, d of w h square. Now, this is again writing it as the sum of a series. Writing it as a sum of a series, what do we have? We have w this minus this squared. Now, let us take any arbitrary term of this. This expression all of us know is distributed as a standard normal variate, as a normal variate with a mean of 0, and a variance of t upon n, because the difference between them is t upon n. Therefore, they are distributed as n 0, mean of 0, variance of t upon n. Each of these without the square, the increment, each of this increment is distributed as n 0 t upon n. Therefore, what does it mean? It means that if I divide this expression by t upon n as I have done here, then I get a standard normal variate, because this numerator is distributed as n 0 t upon n. So, I divide by root t by n and I get this standard normal variate. Suppose if I were to multiply this by t upon under root t by n, I would get a normal variate with a mean of 0 and a variance of t upon n. So, by dividing by root t by n, I get a standard normal variate. Now, what is the value of the mean of a standard normal variate? That is the next question, that is shown here. E of z square is equal to E z whole square plus variance of z, because variance of z is equal to E of z square minus E z whole square. This is 0. Therefore, what is variance of z? Variance of z is 1. Therefore, E of z square must be equal to 1. Hence, what do we have? This series comprises of summations of squares of normal variates, squares of normal variates. Okay. Squares of normal variates of what property? We have z under root t upon n. This is z I under root t upon n. This is one such variable, square of course. This is one such variable. This has a mean of z square has a mean of 1. Therefore, this whole thing has a mean of t upon n. And because there are n such terms in this summation, you multiply by n, each of them are identical in terms of distribution and have the same mean, and are independent of course. Therefore, this n cancels out and we have t as the expected value of this expression. Which expression? This expression. The expected value of this expression is equal to t. Just to recap quickly, this expression can be written as this expression is a normal variate with a mean of 0 and a variance of t upon n. Therefore, this expression when you divide by root t by n is n 0 1. And therefore, we also know that the expected value of z square is equal to 1. Now, the expected value of z square is 1. Therefore, the expected value of z under root t upon n whole square will be equal to expected value of, you see this is non-stochastic, t under root t upon n is not stochastic. So, this becomes t upon n into expected value of z square, and expected value of z square is 1. So, this becomes t upon n. This is for 1 z, this is for 1 z, and how many z's are there? There are n terms in this. So, there will be n z squares here, and for therefore, the expectation value of the sum of n such variables will be t upon n into n, which will be equal to t. In other words, the expectation value of this is t. Therefore, what do we conclude? We conclude that this expression does not hold, is not correct for functions of Brownian motion. In other words, the Newtonian calculus is at a broader perspective, Newtonian calculus is not the correct description of Brownian motion calculus. We need to devise or we need to revise Newtonian calculus in order to describe or in order to do calculus with functions of Brownian motion. The Newtonian calculus that we have does not fit in with the Brownian motion. Why? We will take it up in the next class. Thank you.